All right, buddy. Very short and easy lesson today. Not that big of a deal. I don't want to spend a lot of time on it, but it is electron configuration. So long story short, let's just look at any of these. Let's just look at, like, say, fluorine. Fluorine we know has 9 protons, 9 electrons. Up to this point, we've talked about the idea that fluorine, 2 in the first, and 1, 2, 3, 4, 5, 6, 7 in the next. So, a little tired, sorry. So what we're gonna do is we're gonna talk about what these actual electrons are doing, not just that they're in these shells, but more specifically what they're doing. And the reason why, plain and simple, is the more we understand what the thing they're actually doing is, then the more we can explain how they're gonna behave, like how they're gonna actually interact. So, long story short, we say these 2 electrons here are in an S subshell. So they're in an S subshell. And what that simply means is that these 2 electrons are here. Here's my positive center. We say that they're traveling in a spherical type manner around the nucleus. Now, they're really not. This is where their highest probabilities are. They're not really traveling like this, but we say they are. Then what we have is in the second energy level in our valence shell for fluorine, we're gonna have 7 valence electrons that we're gonna need to figure out what to do with. And what we're gonna say is that those 7 electrons right there, we're gonna have 2 of them in an S subshell. And so we have 2 of them traveling in the spherical type way out here. But then, because we want to try to maximize attractions and minimize repulsions, we want to keep these guys as close together as possible while keeping the negative charge repulsions as far away from each other as possible. What we say then is that we have ourselves the next 5 electrons are going to be in these P subshell, these P orbitals. So we have a P. And what we're going to say is we're going to say that the first one is going to be traveling in a dumbbell-like shape, like that. Once again, these are just areas of high probability. We have another one that's traveling, and please understand there's air quotes every time I say traveling. They're just areas of high probability. They're actually found in these nodes out here. They really don't go through the center like that. They're in these nodes out here. And then we're gonna have another one that's coming in and out in this Z orientation. So we have ourselves these electrons found in these P subshell, these P orbitals in this subshell, these P subshells. So now we can go back through and we can say we have 2 electrons in that first S. And then in the second energy level, I'm gonna draw it up here. We're gonna have 2 more electrons right there. That represents, so the first one is this guy right here. The second one, second energy level, are out here. And then we're gonna represent with the black dots, because this is 1 first energy level, S orbital, in the subshell's S, and we've got 2 electrons in that orbital. Second energy level, S subshell, we got 2 electrons there. Now what we're gonna do is we got 9 electrons total, We got 1, 2, 3, 4. We're gonna go ahead and go 1, 2, 3. This is gonna represent that orientation, and this orientation. Now, once again, it doesn't really matter which one you put first. This we would say is X, Y, Z orientations. So we're talking X, Y, Z. It doesn't really matter which one's first. It's a 3D world. But what we have is we've got a P, and a P. So it's a P subshell, and that subshell, the P subshell, actually has 3 orbitals that make up the P subshell. So this is a p orbital, p orbital, p orbital, p subshell, s subshell, one orbital in it. So an orbital is an area where electrons can be. So we've got 1, 2, 3, 4, 5, 6, 7. Now, why do we do that? It's what's called the Hund's rule. Basically, we're gonna fill up an orbital before we go back through and put it, we're gonna put one electron in each orbital first before we go back through and fill it up. Why? Because once again, we're trying to minimize repulsions. And so we're gonna put a negative charge in one orbital before we put another one, and we put another one in another orbital, and another one in another orbital before we go back through and double it up, because that would cause more repulsions. So by doing it this way, we keep those negative charges as far apart from each other as possible, but remember, those negative charges are wanting to be as close to the nucleus as possible, so we can go back up and we're gonna fill in 1, 2, like that. And it doesn't matter where it goes, you'll be fine. If you see a thing like this, that is allowed. We didn't break any rules there. If you see a thing written like this, that is fine. Didn't break any rules there. But if you see something written like that, now that would be a violation. Of course, this would be fluorine, but that would be a violation. All right, we wouldn't have anything like that. We would want to minimize those repulsions and put another one out there first. Not really a big deal. So now what do we have? We have ourselves 2 electrons in the first. We have ourselves 2 plus 5, 1, 2, 3, 4, 5, 6, 7. 7 electrons in the last. Typically, we don't really do this in AP Chem, but typically we think of this top guy right here being your S, and then these are your P's. Really not that big of a deal on our Lewis structure here, but right here you can see that what we have with fluorine, we have the ability for fluorine to gain an electron right there. And so it can gain one more electron right there. And since all those P shells, those P orbitals are filled up, we can't put any more in that second energy level. So therefore we can put one more. We're going to put another shell up here if we were some other type of element. If we were going to have more than 10 electrons, we'd have to go up to a third energy level, and that too would be an S. So we go to our handy dandy little chart. And we've all seen this, don't really need to go over this very much, but this is your S block, that's your S block. This is your P block, except for helium, that's your P block. This is your D block. And this is your F block, which we almost never use for anything. Now, with the D block, once again, we have 1s1, 1s2, 2s1, 2s2, 2p6, 3s1, 3s2, 3p6, 4s2. But what happens is, because this guy gains another proton and that third energy level is pretty big, we can go back in with that extra positive pull in and the size of the third energy level, we can make a D subshell. So we can come in and do a D subshell, which I'll come back and do in a little bit.